Here is section 2 of the Specialist Maths 2012 Exam 2 paper. We did this as a practice exam, and here are the solutions. Okay, let's do it. So we've got this problem, question 1. Okay, a curve is defined by the parametric equations. X is a cosec function and y is a cot function. Part A says, show that the curve can be expressed in Cartesian form. Okay, now if you look at that form, that is the shape of a hyperbola equation. Okay, so let's see how we can form that. First off, from the first parametric equation, we can rearrange it for cosec. And then square both sides and we get a cosec squared part. Now, that is good because I can use a cosec squared in a trig identity. And the same for the other side. Y on 2 is equal to cot theta. Okay? And square both sides. And there's my cot squared. And now the trig identity is, I've got my cosec squared minus cot squared is equal to 1. And so by substitution, I obtain the Cartesian equation. Okay, next we are going to sketch the curve defined by the parametric equations. Now from part A we got the Cartesian equation, and we're going to use the Cartesian equation because if you have a look, this is in terms of x and y. Okay, very important. Okay, so what do I know about our hyperbola? Well, it has a center of 1, 0, okay, and it's got vertices. Okay, this is the h minus a for the x and the h plus a, okay, parts. So I get 0, 0, and 2, 0 as my vertice coordinates. Okay, and I also will have asymptotes in a hyperbola. So I use the formula for finding the equation of a line, and I've obtained that, except we're not having a square there. I don't know why I wrote a square. That's not a square. Let's get rid of that. Okay, so using that formula, that's my B number, the 2. Okay, that comes from this bit here. Remember, I can do that by, there's my B number there, over A. A is that, it's over 1. Okay, and then that gives me 2 equations. There's one by expanding, a positive 2 and a negative 2. Alright, so let's plot those points. There's my vertices, okay, and there's my asymptotes. So just carefully sketching your straight line, passing through your y-intercepts, of negative 2 and positive 2, and using a gradient of positive and negative 2, and sketching carefully the hyperbola. Make sure you label the equations, each asymptote with their equation, okay, and we will get a full marks if we have it written like that. Okay, let's try the next one. Alright, so the region bounded by the curve and the line x equals 3 is rotated about the x-axis. Find the volume of the solid formed. So this is the solid revolution, okay, and if we look at the previous example, we're finding the region that is from the curve to x equals 3. So there's x equals 3 there. And what is this region here? And we can see the limits of this region is going to be from 2 up to 3. Okay, so that's very important. So we will have, there's our formula to find the volume of a solid revolution with those limits from 2 to 3. Okay, and y squared can be taken from the equation of the hyperbola. Okay, and we substitute that in. Yes, and from there we can, using that integral, we just evaluate that on the CAS. We get our result. Okay, so make sure all you need to do is just set up your integrals and write them in the space provided on the paper, and then all the calculations can go ahead and be done in the CAS. You don't necessarily have to show the working out steps and how to solve an integral. Okay, make sure you use that CAS wisely. Alright, the next bit, find the gradient of the curve when theta is 7 pi on 6. Alright, so the gradient is found by using the chain rule. So we're finding the curve of the hyperbola, the gradient is dy dx. Alright, now that's found by using the chain rule of using the gradients of the parametric equations. Now this second one here, d theta dx, well, that is simply just the reciprocal of dx d theta. So differentiating the first parametric equation with respect to theta and taking the reciprocal of it. That's what we're going to be doing there. So let's find that. dy d theta is given by this. Now that's taken by differentiating the cot function. Okay. And then the next one here is dx d theta. So we go ahead and substitute that into our chain rule formula like we've done there. Okay, and simplify it to get 2 over cos theta. Okay, then we have to work out, well, what is it going to be at theta equals 7 pi on 6. So we substitute that into our rule, and we do that calculation in the CAS. We get -4 on root 3. Okay, very good. Next. Okay, now complex numbers, question 2. Now, given that cos of pi on 12 is this third, alright, shows that sine of pi on 12 is equal to that third. Okay, now you got to come up a way that links cos of an angle and sine of an angle, and we're going to be using the trig identity. So sine squared of the angle pi on 12, well, that's 1 minus cos squared of the angle. So we show that carefully as a calculation. 1 minus, there's the answer for cos, and we square it to obtain this, and we can form a common denominator of 4, so we get 4 on 4 here. And finally, we obtain that for sine squared. So that there is sine squared, and we go ahead and square root to get oh, that should be here. But now what we've got for sine. Okay. So sine is just the square root of that value. And now we just got to remark that since we're looking for sine is positive, being an angle in the first quadrant, then we only take the positive square root. So it's important just to state that, because when we square root both sides, remember we get the positive and the negative square root, and we have to decide which one is correct. And in this case, it's the positive square root because sine is positive for angles in the first quadrant. Very important to remember to do that. Alright, part B, express this complex number in polar form. Now, if you look at the thirds given, the real part and the imaginary part, okay, it's these things there and there, that's the same as what's given up here. That's the real part and that's the imaginary part. And we've got the cos and the sine equivalents for it. So Z1 is cos of pi on 12 plus I sine of pi on 12. Okay, and expressing that in cis form, there we go, Z is cis of pi on 12. Okay. Now, part 2 of this question, write down Z1 to the power of 4 in polar form. Now, any complex number to a power, we use Demoivre's theorem, and the 4 becomes a multiplying factor of the argument. So we're going to have 4 times pi on 12, and that's just simplifies down to pi on 3. Cis pi on 3. There you go. Okay, now this one, let's think about this carefully. This notation here can be quite confusing. So let's just break it down. The first bit, where we've got the squiggly brackets, that's a list. Okay, looking at a list of values. So we're after a region of arguments. Okay, in between you've got a domain of arguments here, the argument of z1 and the argument of z1 to the power of 4. Okay, now from the previous questions we worked out what those arguments are. We had pi on 12 for just z1 and pi on 3 for z1 to the power of 4. So that's the first bit. And if you look on our argand diagram, it's broken up into 1, 2, 3, 4, 5, 6 divisions for a quadrant. So think about 90 degrees divided by 6. Each is in fact going to be 15 degrees, which is pi on 12. So it's a pi on 12 equivalent. And this one there is pi on 12, and up here that would be equivalent to pi on 3. So we've got a range of angles first, going from pi on 12 up to pi on 3. Now the next bit here looks at now a radius, which is the modulus or magnitude of z, all right, from 1 to 2. So that is z equals 1, that's this circle. Z equals 2 is that circle. Okay, so identifying the region where all this crosses, that's the intersect, all right, where the arguments and the radius cross, is this part here. Okay, this little part of a sector. Okay, and we're going to shade that in carefully. Alright, so most important, we shade it in fully and don't leave any parts uncolored in, unshaded, especially the corners. VCAA really wants you to get these corners in shaded sharply. They're very pedantic about that. Okay, alright. The next part looks at find the area of the shaded region. So what region did we have was in fact like a shaded region found of the subtraction of two sectors. Okay, now the area of a sector, okay, is given by this rule. So you take the angle of the sector as a fraction of 2 pi or 360 degrees times the area of a circle. And we've got two of them. We've got the sector with radius of 1 and a sector with radius of 2. Okay, now the angle of that sector is the difference of the arguments of the two complex numbers. Okay, the larger angle, pi on 3 minus pi on 12, and that gives you a pi on 4. Alright, so that's the size of the sector. Alright, now that simplifies down, pi on 4 on 2 pi simplifies down to an eighth. And we find our two radiuses, r equals 1 and r for r2, giving a radius of 2. And we get our two areas of the sectors, and the shaded region is now the subtraction of those two areas. There it is, 3 pi on 8 units squared. Okay, now part E. Find the values of n such that the real part of complex number z1, okay, to the power of n is equal to 0. Alright, so here is our complex number z1. That's given in Cartesian form, but in the previous question we worked that out to be in polar form. So first off, we're finding the real part of z1. Now z1 to the power of n, using Demoivre's theorem, the n just multiplies the argument. There it is, n times the argument, and z1 is the cis of pi on 12. Now the real part of cis of pi on 12 is cos. So there we go, the real part of the complex number cos n pi on 12, we have to equate that to 0. So that's setting it up there. Now we go ahead and solve. Now what we have here, in fact, is the inverse cos of 0. Now we got to use the general rule for solutions, because a circular function is continuous, and so every revolution of 2 pi, you've got another solution. So we have to plus 2k pi each time. Now k is just some integer, it's some counter. Okay, so there's your general solution for the angle. Now inverse cos of 0, well, that's pi on 2. So let's work out what we'll have for n is equal to, there we go, there's what n is, 12 on pi times that. Okay, solving for n. And then when we simplify, we get 6 plus 12k. Okay, just by expanding the brackets there. And just state again what k is at the end. K is an element of the integers. So this is your general solution for n. That's what we're after. Now, for z1 to the power of n, find z1 to the power of n for values of n found in part 1. Alright, so using our rule for n that we worked out in the previous part. Okay, now we're doing it for the whole complex number cis. Okay, not just the cos part, but cis of n pi on 12. Now, we've got 2 parts. K is 0, so n equals 6 plus 12k, where k is 0, and that gives us n equals 6. So the first one is working out z1 to the power of 6. Substitute that in to the cis function here, and that's cis of pi on 2. And cis of pi on 2, remember, cis is cos of the angle plus I times sine of the angle. Cos of pi on 2 is 0, and sine of pi on 2 is 1. So 1 times I gives you your I. Okay? And then we've got to do that for another k value. K is equal to 1. We're going to substitute that for n, and we get n equals 18. So we're working out z to the power of 18. And cis of 18 pi on 12. That fraction simplifies down to, well, that's just cis of 3 pi on 2. Okay? Now cos of 3 pi on 2 is 0. Sine of 3 pi on 2, that is negative 1. So we're going to get a negative I value for cis of 3 pi on 2. We need to be able to calculate that really quickly. Okay, that could be done, if you're unsure about your cos and your sine values of angles, do it on the CAS and then record your result. And there we have it. And we will find they are our only unique values. Let's go back a little bit. They're the only unique values of z1 to the power of n. It's plus I and minus I. There's no others. If we go k is equal to 2, okay, we'll have n is equal to 30. Okay, and if we put that in, we're going to get another result, and you'll have cis of that angle will give you I, and then the next k value you'll get a value of negative I, and it will just keep changing I, negative I, and the only unique values are those ones. Okay, done. Let's look at the next part. Question 3. Okay, so a car accelerates from rest. Okay, so rest means u equals 0. Its speed after t seconds is v. Alright, so this here is, as it's accelerating, the velocity, or the speed as it accelerates at any value of t is given by this rule. Okay, so write down, part A, write down the limiting speed of the car as t approaches to infinity. Alright, so the limiting value of v. This basically says, well, as t increases and approaches infinity, what happens to first the inverse tan function. So this tests your understanding of implied range of the inverse tan. Okay, so an inverse tan, look on your formula sheet, inverse tan ranges up to pi on 2. Okay, so as t approaches infinity, inverse tan of the angle approaches pi on 2. Okay, so then that means for v now, as t approaches infinity, v is going to approach 17 multiplied by pi on 2. 17 pi on 2 meters per second. There we go. Okay. Part B, calculate, correct to nearer 0.1 meters per second squared, the acceleration of the car when t equals 10. So first let's find the acceleration. Acceleration is dv dt. So do that in the CAS and we'll get this expression. Okay, so we just record what we obtained down on the CAS, and then at t equals 10 we're going to do that substitution into our expression for acceleration. Alright, and we will obtain that result. So all this calculation is just simply done on the CAS. Okay, where we have here the t squared, just on the CAS replace that t with a 10. So in the denominator you'll have your pi squared multiplied by 100 plus 36, and that's the calculation we need to have done. Okay, and we would obtain this amount. And then write your answer according to the requirements of the question, nearer 0.1, and we'll get acceleration equals 0.3 meters per second squared. Okay, good. Next part, part C. Let's calculate, correct to the nearest second, the time it takes for the car to accelerate from rest to 25 meters per second. So you're thinking, alright, the car is accelerating, we have to use the acceleration function from the previous part. That's not quite true, because the car is accelerating from rest to 25 meters per second. That's the speed that's given, 25 meters per second. So our function for speed as the car accelerates is what we need, and we need to calculate for when the function is equal to 25. So we solve the function, the inverse tan function equals 25 when v is 25. We solve for t, we write that down, that's our method, we do that on the CAS. So set that up as a solve function on the CAS, hit enter and record your time as you see it on the CAS. Then give your answer correct to how the question wants it. Okay, nearest second, there it is. So we rewrite it, t is equal to 19 seconds. Okay, and that's all we need to do to obtain 2 marks. Alright. Next bit. Now, after accelerating to 25 meters per second, okay, so car's accelerated, it's gotten this speed. The car stays at this speed for 125 seconds. So it's maintaining 25 meters per second for 120 seconds. So there's a bit of a distance covered there, okay? It then begins to decelerate while braking. Alright, so this is another part of the journey. The speed of the car, t seconds. So see how this is small t compared to the previous question, it was a capital T. Think of them as 2 different periods of time. Okay? So the speed of the car, t seconds after the brakes are first applied, is v. Now here's the expression. This one is an acceleration function, dv dt. There it is. So this is decelerating. This is the deceleration function for braking until the car comes to rest. Alright, very important. Now let's find v in terms of t. We want to know what is the velocity as the car brakes. Alright, so we're setting up a differential equation. First off, we draw on this information. Here is some initial condition. When at the start of braking, we're traveling at this constant speed of 25 meters per second. So velocity is given by this integral, okay? differentiate with respect to, integrate with respect to t. Take that negative 100 out the front, and when we integrate, it's just a power function, so it's 145t minus t squared plus c, integration constant, don't forget that. Alright, now we use our initial condition, when t is equal to 0, we get v equals 25. Okay, and that gives you a c is equal to 25. Nice and easy. And put it all together, there it is, for full marks. That's all that's needed. Okay, very good. Next part, find the time in seconds. Okay, taken for the car to come to rest while braking. Alright, so we're after a time for velocity to come to rest for velocity is equal to 0. So we solve the velocity function equals 0 for t. Okay, we set that up on the CAS using a solve function, and we hit enter and we get our result. T is equal to 20 seconds. Very good. Nice and easy. Okay, so we're doing well. Let's look at the next bit. Party. Write down the expressions, plural, for distance travelled by the car during each of the 3 stages of its motion. Alright, 3 stages of its motion. So the first stage was when the car was accelerating. So this is the first part of the problem. So we're accelerating. Okay. So this here is the velocity function as the car accelerates at any point in time t, capital T. Okay. So we had from the endpoint 0 to 19. Okay, it's 19 seconds taken from the previous part in the question. Okay, and we can see, well, that was part here, this one, where the time it takes for the car to accelerate from rest to 25 meters. Okay, so that's the only the amount of accelerating the car does, and we get t equals 19, so we've gone ahead and we've used that. Okay, so that's stage 1. From distance is the integral of the velocity function, and we want to do that from 0 to 19 seconds to get the distance travelled. Okay. Then stage 2 is a constant travelling for 120 seconds at some constant velocity. So that's this piece of information here. We've accelerated up to 25 meters, and then the car stays at this speed for 120 seconds. So distance is the velocity, the speed, multiplied by the time. Okay. So 25 times 120. And then the next part, stage 3, this is when now the car's braking, the deceleration. So it comes to rest. From the previous question, we worked out, well, it comes to rest at t equals 20 seconds. Okay, now this is a new t, so a new stage of the journey, the deceleration stage, the braking stage, and we're using small variable t instead of big, so new stage of braking. So it's going to be from 0 to 20 seconds of braking. Okay, and there it is. So again, it's an integral of the velocity function to get distance travelled, and we want for t from 0 up to 20 seconds until it comes to rest. Okay, so there's parts, that's the first distance travelled for stage 1, stage 2, and stage 3. Okay, each part is a distance, the integral of a velocity. Okay. Whew. So trying to piece all that together, you really got to read all the question in full very carefully and go back and reread it again and piece it together very carefully. just takes care and for you to stay calm and relaxed as you're doing it, so you're not making mistakes. Okay, find the total distance traveled for when the car starts to accelerate to when it comes to rest. So this is the 3 stages: accelerating, so it's going up, and then it travels at a constant velocity, and then decelerating again down to rest. So we set this up as a total distance traveled all together. So this is the addition of the 3 expressions. Okay? Part 1, Part 2, and Part 3, Stage 3 of the journey. There it is. So there's your expression for total distance traveled. Now, all you need to do now is set that up carefully in the CAS. You don't need to show any working out steps. Okay? Set it up, because this really, have a look, it's only worth very little amount of marks. It's only worth, there it is, 1 mark. So do that in the CAS and we get that result. Give your answer to the nearest meter, and there it is. Okay. Whew. Okay, we can get tough questions, so you just got to read through them very carefully and think about it very slowly. Okay, well done. Question 4. So we've got a position vector of the International Space Station when visible above the horizon from a radar tracking location. So that's at point 0 there. So this first line is the horizon of Earth at point O, and the position vector, there you go, is your J component, I component, and there's your R of T, position vector to S, the International Space Station. Okay, and there it is. It's a hefty looking position vector of sines and coses. So we've got to be careful working with such a thing, writing it down carefully each time and just doing all the calculations on your CAS. It's across a restricted domain. I is the unit vector relative to O as shown, and J is the unit vector vertically up, straight up. Time T is measured in hours and displacement in kilometers. So find the height, H, kilometers, of the space station above the surface of the Earth when it is at point P directly above O. So the height. So directly above O is way up here. Now, at point P, the I component, okay, is 0. So x of t, which is the first part there, well, that is 0 at P. So that's the first thing. At point P, x of t is 0. So if we go ahead and solve x of t for 0, alright, when that is equal to 0, we solve that for t and we get, there it is, value for time. Okay, so this is the time when the International Space Station is at point P. Now we have to go determine the height, and the height is found by using our value for t and substituting it into the vertical component. Okay, so h is given by, there it is, the vertical component, there it is, whoop, and we're going to solve that, we evaluate that, making sure you substitute your t in there, and you get 400 meters, and you just do that on your CAS. Okay, very good. Alright, part B. Find the acceleration of the space station, alright, and show that its acceleration is perpendicular to the velocity. Alright, so from the position vector we have to first get the velocity vector. So just doing the derivative on your CAS carefully, entering each term carefully, and we just write it out on your CAS. Now it's more easy not to substitute in and evaluate 3.1 and so on for pi. Just use a full multiple of pi, and you just go ahead and take this 1.3 times the 6,800 in your position vector to get this value, and just work in whole numbers. Okay, so there's your velocity vector. Then we go ahead and differentiate again to get the acceleration vector. There it is, and again, just keep the whole multiple of pi out the front. We got pi squared this time. Okay, and then basically we're just taking this 1.3 and timesing the 8,840 to get that number. Okay, so perpendicular, when velocity and acceleration are perpendiculars, when we've got the dot product of our two vectors. Okay, and we have to show that our dot product equates to 0. So we'll go ahead and perform the dot product. Okay, and just now we've got a very long expression to write down, so we can just make it a little bit more easy for ourselves. Instead of writing the full argument of sine and cos here, we're going to just do a little substitution, write it as u. Okay, and we're going to state u out here on the side, and that just allows us more room to write down. Okay, and again, when we do our dot product, we're performing, this multiplication. This is a pretty big number, 8,840 times 11492. Okay, you can express it in a simple way as just something like this. Now, I did the square root of the number and then I squared it, and I've got it as the third squared. Just an easy way, convenient way of writing it down so we can fit it in the space. Okay, so the point of this type of question is to challenge you, to get you to think about how can I communicate my numbers in an efficient way, because we've got limited space. Okay, so there's our dot product, and we can see things are the same. We've got the same cos u sine u, there's cos u sine u, and you've got a negative of the number and the positive of the number, and we can see that definitely goes to 0, and then hence therefore our vectors are perpendicular. Okay, fantastic. Part C, find the speed of the space station in kilometers per hour. Okay, speed, right, so speed is the magnitude, the modulus of velocity vector. So we got to set up our velocity vector, write that down as we determine it from the previous question that we got from the CAS, and we take the modulus. Okay, so we square the x component plus square the y component and then square root. And we will notice that we've got a cos squared plus sine squared, okay, which go to 1. So you've simply got 8,840 pi squared, then the square root, and then when we evaluate that, we've got this value for speed, kilometers per hour. Okay, 27,772 kilometers per hour. That's pretty fast for the International Space Station, and it's quite realistic actually. Very good. Now, part D, find the equation of the path followed by the space station in Cartesian form. Okay, so finding the equation of the path from a position vector. Okay, so this is where we break down our position vector into an x function. There's x, and there's y. Okay, and there's now, we've got our Cartesian variables, x and y. Okay, and we got to apply these two in a similar way, making use of sine and cos. And there's a good thing involving sine and cos. It's called a trig identity. So there's an expression for sine, x on 6,800, and rearrange and determine expression for cos. There we go. And since sine squared of an angle plus cos squared of an angle equals 1, beautiful trig identity, then we apply that to the left hand side of our above equations, and there we have it. That is, look at that, That is in fact an equation of a circle. A circle. Okay. And it's a circle that has a radius of 6,800 kilometers. Very good. Next question. Find the time when the space station is at a distance of 1,000 kilometers from the radar tracking location. Okay, point O. Give your answer in hours. Alright, this time we're finding a distance. Now, distance is a scalar quantity. So far, the only information we have are vectors. We've got a position vector. How do we find distance from a position vector? Well, your distance essentially is the modulus, the magnitude of the position vector. So that's the first thing. Write down your position vector with the I and the J notation, and we're going to take the modulus of it. Okay? So we square the x component plus we square the y component. The y component is that whole bracket, and we square root. Okay, now we're going to evaluate that on the CAS. Okay? And we got to then equate that to distance is equal to 1,000. Now, when you go ahead and expand the brackets and you evaluate on the CAS, we're going to get something similar to this. Okay, so just write down what result you get on the CAS, or an equivalent form like I have written here. Just it's a simplified expansion of the brackets inside the square root, and then I've squared both sides to get equals to 1,000 squared, being the distance is 1,000. And again, I've just written it in an efficient way with using U notation. There's U. Okay, where U, and we got to state what U is whenever we use such a notation. All right. Now, first we want to simplify that. We want to solve that for cos of U. Okay, and we're going to obtain this as a result. Now, I just plucked that straight from the CAS. I set that up, this expression here, as a solve function on the CAS, and that is my method I used, and I obtained that. Then I solve this for t, okay, where t is across some restricted domain. That's from the information at the start. So again, I set up a solve function of this expression here in the CAS, and I go solve for t, and then I include my restricted domain. If I don't do that, I'm going to get some general solution that the CAS is going to give me. Okay, so I solve across my domain, and there's my time, my two time values that I have to state. Very good. And giving you in hours correct to 2 decimal places. Done. This is really about following a method and communicating our steps, but doing all the calculations on the CAS. Oh, wow. All right, we're almost there. Question 5. At her favourite fun park, Catherine's first activity is to slide down a 10-metre long straight slide, and she starts from rest at the top and accelerates at a constant rate until she reached the end of the slide with a velocity of 6 meters per second. Well, I like the idea that it's a constant rate because I'm going to use my constant acceleration equations. Very good, kinematics equations. First one, part A. How long in seconds does it take for Catherine to travel down the slide? Okay, now the slide is 10 meter long, straight slide. Good, so x is 10. Now, we've got, she reaches the end of the slide with a velocity of 6. So that means v is 6. And she's starting from rest. So that means u is 0. So x, u, and v, and t is this formula. We substitute and we solve for t. We get 10 over 3 seconds. Okay. Next part. When at the top of the slide, 6 meters above the ground, okay, Catherine throws a chocolate vertically upwards. Now, anything that's thrown vertically upwards is going to go up, and then it's going to go down. So the chocolate travels up and then descends past the top of the slide to land on the ground. You got to think about, where is Catherine in all this? She is actually on the top of the slide, 6 meters above the ground. Assuming that the chocolate is subject only to gravitational acceleration, that air resistance is negligible. So that means constant acceleration. Alright, now how are we going to interpret that? Here's a little diagram to help us think about it. Now, the red part is the slide. The blue part is the path of the chocolate going up at 10 meters per second and then coming down. Now, the black line is like, think of it as your zero location, your reference point. This is the origin. That's the top of the slide where Catherine is standing. So, up is positive, okay, as denoted by the positive 10 meters per second. And then going down below this line, you've got to think in vectors, because you've got to think about, we've got a displacement going on here. We've got a displacement of negative 6 meters, okay, because you've got to think about what that chocolate is doing. The chocolate is going up, okay, up to some maximum height and then down, back to this zero location. So far the displacement is 0. Then we're going down another 6 meters. So it's a negative displacement of 6 meters. Okay, got to remember, x is displacement. It's not a distance, and a displacement is a vector. Very, very important. Okay, so we set up with this rule. Okay, now x is negative 6. U is your initial velocity of positive 10 meters per second. And A is gravity, acceleration due to gravity. That is going down, and down is negative. So we're going to have a negative half of 9.8, which is your negative 4.9. Alright, so we've set that up carefully. Now we go ahead and solve for t, and we get t is 2 values. There they are. Okay? Now, we have to realize that, hang on, t is time, and t has to be greater than 0. So the negative value of t is not correct. Therefore, we use correct to the nearest tenth of a second. T equals 2.5 seconds. And there's our answer. Wow, so we've got to be very, very careful. What I have to emphasize about this question is the whole concept of x in this formula here. X is displacement. Displacement is a vector, and it's going to have a negative value, being below a certain position. Below a starting position is going to be negative. Above a starting position is going to be positive. Okay? Whew. Next bit. Assume that it takes Catherine 4 seconds to run from the end of the slide to where the chocolate lands. At what velocity would the chocolate need to be propelled upwards? If Catherine were to immediately slide down the slide and run to reach the chocolate as it hits the ground, to give your answer in meters per second correct to 1 decimal place. Alright, this bit here, assume that it takes 4 seconds to run from the end of the slide to where the chocolate lands. So we've got some time of running from the bottom to catch the chocolate, and then you've got the time from the top of the slide and sliding down to the bottom, which we worked out previously in the first part. So that's what the chocolate's doing, going up and it's going down. And the girl, Catherine, she's sliding down from the previous question, 10 out of 3 seconds, and then she's running from the bottom of the slide over here to catch the chocolate, 4 seconds. So what's the total time? 10 out of 3 plus 4, which as an improper fraction, 22 over 3 seconds. We've got to use that. And again, what is the displacement that the chocolate bar does? Okay, so as the chocolate bar travels up and travels down, your total displacement is a -6, just like the previous question. Okay, and this is the time that the chick Catherine has to achieve, 22.3, same as displacement. What is going to be the initial velocity u to obtain such a displacement for a time 22 over 3? So put in your values and solve for u, and we do that on the CAS. U equals 35.1 to correct to 1 decimal place. Make sure you read the question properly and you always answer it according to the instructions of the question. Alright, we're coming to the last part. Catherine's next activity is to ride a mini speedboat. Okay, now to stop at the correct boat dock, she needs to stop the engine and allow the boat to slow by air and water resistance. Okay, at what time, t seconds, after the engine has been stopped, the acceleration of the boat is related to velocity. Here we go. So we've got acceleration in terms of velocity. Here's some more information about the problem. Catherine stops the engine when speed is traveling at 7. Okay, so that means when t is 0, we're going to get velocity of 7. So first let's set up our dE. We've got a differential equation. Acceleration is dv dt. That's the first bit. dv dt is given by this function of v. Now let's solve our differential equation. We can separate our two variables. We've got all the v's on the left and the t on the right. And then we integrate. It's just important to just put only the v parts that's relevant to the function, the v function, all on the left, and any other thing like this -10th, not needed in your v function. It's going to join the t part over here. Now it's good to try and think about that and get in the habit, because that makes the solution easier to solve. Now let's look, can we recognize what this function is here? That is the derivative of an inverse tan. So the integral, inverse sine. So your integral gives you inverse sine of v on 14, and if you're unsure you can look it up in the formula sheet or just do that on your CAS. Okay, integrate with respect to t on the other side plus c. Don't forget that integration constant. Always, just for simplicity, put that plus c with the t side of the equation. When t is 0, v is 7 from our initial condition here. We substitute that in. We get inverse sine of a half, which is pi on 6. So substitute that back into the equation. There it is, and we transpose for v. We take the sine over both sides. V is 14, sine pi on 6, take t over 10. There it is. Whew. Okay, find the time it takes the speedboat to come to rest. That means v is 0. Give your answer in seconds. Okay, so v is 0. So we solve the equation we determined for velocity. We let it equal to 0 and we solve for t. We write that down. That's our method. Okay, and we set that up in the CAS and we solve for t. There it is, and we just give it as a radians in terms of pi. 5 pi on 3 seconds. Done. Find the distance it takes the speedboat to come to rest from when the engine is stopped. Okay, give your answer in meters correct to 1 decimal place. Let's do this. V is dx dt. Okay, and there's our velocity function we determined. So dx dt is equal to that. We're setting it up another dE, and this time we're going to work out what is the distance. So x is the integral of the velocity function. Now have a look at because we're finding the distance traveled or the distance it takes, here we're going to evaluate at endpoint straight away. From time of 0, that's the start when you turn off the engine, up to this time from the previous question. This is when 5 pi on 3, when it comes to rest, velocity is 0. What is the distance traveled there? All you have to do is set that up now in your CAS and evaluate. 18.8 meters, correct to 1 decimal place. Make sure you follow the instructions of the question. Okay? So, not more is needed. You don't need to write anymore. It's as simple as that. Okay? For 3 marks, there it is. You get 1 mark for setting up the problem with for x with the integral, 1 mark for the correct terminals, boom boom, and then 1 mark for the answer. Whew, and I think we have finished. Well done. Well, exam 2 is a tough exam, and I hope you can use these solutions to review your own answers. If you're unsure about certain things, please ask questions, and we will keep studying. Well done, everybody.